Title: The Complex Logistics of Air Traffic Control. Primary engineering angle: civil infrastructure, logistics, systems engineering, network constraints. Opening hook: the constraint. On March 27, 1977, two fully loaded Boeing 747s collided on a runway in Tenerife. 583 people died. There was no engine failure, no structural collapse, no wing tearing apart mid-air. The airplanes worked perfectly. The system failed. Visual: black screen. Audio of cockpit chatter fading in. Radar screen with two targets converging. At its core, air traffic control is not about flying airplanes. It is about preventing collisions in a three-dimensional space where hundreds of aluminum tubes travel at nearly 900 kilometers per hour. The impossible barrier is this: if two aircraft are separated by just 5 kilometers laterally and 1,000 feet vertically, that margin is considered safe. 5 kilometers. At 900 kilometers per hour, that separation vanishes in 20 seconds. Air traffic control is the infrastructure that keeps that 20-second margin from ever disappearing. And it must work perfectly. Every minute. Every day. Part 1: The context. Why air traffic control exists. Modern aviation is an economic machine. In 2023, over 4 billion passengers flew globally. On peak days, more than 100,000 flights operate worldwide. Visual: global time-lapse of aircraft positions over 24 hours. Without air traffic control, commercial aviation would collapse instantly. Why? Because the airspace is a shared resource. Unlike roads, the sky has no painted lanes. Unlike railways, there are no fixed tracks. Aircraft move in continuous three-dimensional space. So the fundamental challenge becomes: how do you impose order on a volume? Air traffic control, ATC, is essentially a real-time logistics algorithm applied to physical objects with mass, inertia, and limited maneuverability. But before we understand how it works, we need to understand the physics constraints that make it necessary. Part 2: The physics constraint. Why separation is mandatory. Aircraft are not agile drones. A commercial airliner at cruise speed has mass 70, 000, 300, 000 kg. Speed 250 m/s. Kinetic energy 1/2 mv superscript 2. Let's calculate that. For a 100,000 kilograms aircraft, Q equals 0.5 times 100,000 times 250 superscript 2 equals 3.125 billion joules. Visual: equation appearing on screen. Comparison to TNT equivalent. That's roughly equivalent to 750 kilograms of TNT. And that energy cannot be stopped instantly. An aircraft cannot simply swerve like a car. Its turn radius at cruise speed can exceed 5 kilometers. Visual: top-down diagram showing wide turning arc. This means, if two aircraft are placed on a collision course, there is no last-second correction. Separation must be proactive, not reactive. Part 3: The infrastructure problem, imposing structure on chaos. The sky is divided into controlled volumes called sectors. Visual: 3D grid overlay dividing airspace into sectors. Each sector is managed by a controller responsible for horizontal separation, vertical separation, traffic flow sequencing.
But here's the constraint. A single human controller can safely manage only about 15 to 20 aircraft at once.
Why?
Because cognitive load scales nonlinearly. Each aircraft can potentially conflict with every other aircraft. Mathematically, conflict pairs grow as n(-1)/2. So with 20 aircraft, 20 times 19 divided by 2 is equal to 190 possible conflict pairs. That's 190 potential collision paths the controller must mentally track. This is not a radar job. This is combinatorial optimization in real time. Part 4: The hero solution, radar and transponders. Originally, aircraft separation was procedural. Pilots reported positions over radio. Controllers estimated spacing using time and dead reckoning. Then came radar. Visual. Early World War II radar screen transitioning to modern ATC radar. Radar works by transmitting electromagnetic pulses and measuring return time. Distance equals speed of light times time/2. But primary radar only shows a blip. It doesn't identify the aircraft. That's where secondary surveillance radar comes in. Aircraft carry transponders that respond with identity, altitude, squawk code. Visual. Exploded diagram of radar beam interacting with aircraft transponder. This transforms the sky from anonymous dots into labeled, trackable objects. But radar has limits. Line of sight only. Range limitations. Mountain shadowing. Refresh rate constraints. Which leads us to a newer solution. Part 5, ADS-B. The GPS revolution. Automatic dependent surveillance, broadcast. ADS-B allows aircraft to broadcast their GPS-derived position once per second. Visual. Aircraft emitting digital signal. Data link lines connecting aircraft and ground stations. Instead of waiting for radar to sweep every 5 to 12 seconds, ADS-B provides near real-time tracking. This reduces uncertainty. But here's the trade-off. ADS-B depends on GPS. GPS signals are weak. They can be jammed or spoofed. So redundancy remains critical. Engineering reality is about layers of safety, not single solutions. Part 6. The bottleneck, runways. Cruising aircraft are easy compared to landings. The runway is the real constraint. A runway can handle roughly 30 to 50 landings per hour. Why not more? Wake turbulence. Visual. CFD simulation showing wingtip vortices spiraling behind aircraft. As an aircraft generates lift, it creates wingtip vortices, rotating tubes of air. These vortices can flip smaller aircraft. So aircraft must be spaced by time and distance based on weight class. Heavy, medium, light. This means, even if radar allows tighter spacing, physics does not. Wake turbulence dictates minimum separation. You cannot negotiate with vortex strength. Part 7. Flow control. The national airspace as a network. The U.S. airspace system functions like a distributed network. Major hubs. Federal Aviation Administration. Eurocontrol. These organizations coordinate flow using centralized traffic management. Visual. Network diagram of hubs and routes. Airspace congestion behaves like network congestion. If Chicago slows down due to weather, aircraft departing from New York may be delayed before takeoff. This is ground delay programming. Why? Because holding aircraft in the air burns fuel. A jet at cruise burns 2 to 3 tons of fuel per hour. Holding on the ground burns almost none. The economics dictate that we shift delay upstream. Part 8. The human element. Despite automation, humans remain central. Why? Because edge cases dominate aviation risk. Weather deviations, medical emergencies, runway closures. AI struggles with rare, high-consequence anomalies. Controllers undergo years of training to build mental 3D models of traffic. But fatigue is real. A single lapse can cascade. So shifts are limited. Redundancy is layered. This is not a tech problem alone. It is a human systems problem. Part 9. Trade-offs and failure modes. Let's challenge a common misconception. Why don't we just automate everything? Because automation introduces new risks. Software bugs, cybersecurity vulnerabilities, GPS spoofing, system-wide cascading failure. A fully centralized system may optimize efficiency, but it reduces resilience. Distributed human controllers create friction, but friction adds safety margins. Engineering is always compromise. Part 10. The future. Next-gen and satellite control. Programs like the FAA's Next-Gen aim to replace radar with satellite tracking, enable performance-based navigation, allow curved, optimized approach paths. Visual. Side-by-side comparison of straight versus curved descent path. Curved descents reduce fuel burn and noise, but they increase complexity. Aircraft now follow precise GPS-defined paths. Small navigation errors could accumulate. So again, redundancy. Part 11. Comparative Math. Why this system is extraordinary. On a peak day, 100,000 flights, 10 million km traveled, thousands airborne simultaneously. Mid-air collisions between commercial airliners? Essentially zero in modern controlled airspace. Statistically, commercial aviation is safer than driving. But unlike roads, aircraft cannot pull over. Every safe arrival is a coordinated logistical success. Part 12. The economic reality. Air traffic control infrastructure costs billions annually. Radars, satellites, training facilities. But compare that to global aviation contributing trillions to GDP. If ATC efficiency improves by even 1%, fuel savings alone reach billions. Yet expanding capacity is expensive. Building new runways in urban areas is politically and physically difficult. So optimization, not expansion, becomes the path forward. Final verdict. Air traffic control is not glamorous. It is not visible. But it is one of the most complex real-time logistics systems ever built. It operates at the intersection of physics, human cognition, network theory, infrastructure engineering. And it works. Not because it is perfect, but because it respects the constraints of reality. Aircraft have mass. Humans have limits. Wake vortices obey fluid dynamics. Information travels at finite speed. The system is viable. The future will add automation and satellite precision. But it will never eliminate trade-offs. Because no matter how advanced our algorithms become, we are still moving thousands of explosive kinetic objects through a shared sky. And the laws of physics do not negotiate. Visual. Sunset shot of aircraft on final approach, layered radar overlay fading out. Air traffic control is not about controlling airplanes. It is about controlling complexity. And complexity, when left unmanaged, is fatal.